The next talk is going to be given by Pavel Golovin on RELINCHE, automatically checking linearizability under relaxed memory consistency.
Does it work? Yeah. Okay, thank you for the introduction. And I would start my talk with just obvious fact that concurrent programming is quite challenging, because software engineers should think about different aspects like synchronization between threads, safe memory reclamation, and performance. So usually they're using just concurrent libraries. For example, libcds, it's a concurrent library for C++ that is popular on GitHub and providing high-level primitives like concurrent queue, stack, set, and so on. And since it's so widely used, a reasonable question is how we can be sure that such implementations are actually correct. For that, let's take a look on this example of usage concurrent queue. In the first thread, we are pushing value 1 and 2, and second thread, we are retrieving value from the stack. And which possible values we can see in second thread. So right answer is bottom, which is just a marker of empty queue, and 1. But we cannot see 2 or 42. Why it's like this? State-of-the-art notion of correctness for concurrent data structures is linearizability, which is saying that if implementation is linearizable, all its behavior should be explained by executing operations of the data structure in some linear order, which is respecting runtime order. So for example, we can first execute dequeue and see actually empty queue, and then execute enqueue1 and enqueue2. And since we should respect runtime order, we can execute enqueue2 first. This is two other linearizations that is showing that we can also get 1. 2 and 42 we cannot get, so they're considered incorrect. So far, so good, but it doesn't work well for weak memory model context, unfortunately. So here we have two data structures, queue and stack. In first thread, we are pushing value into stack and retrieving value from the queue. And in second thread, vice versa. Question is, can we actually see both of these structures empty in both threads? And it's counterintuitive, but under weak memory model, it's actually, it's not linearizable, definitely, because there is no linear order that could justify this output value. But this is intended behavior under weak memory model, because there is no reason to forbid this. There is no interaction between threads here, no passing data. And if we would forbid this behavior, we just introduce more penalty for performance. So we still want to have atomicity, but only per each object. So if we take a look only on operations on the stack, this is fine, because first we can execute pop and see empty marker, and then execute push. And same for queue. But just atomicity is not enough. Some implementation of concurrent data structures want to provide guarantees on synchronization. For example, here, it's very natural to expect that if in second thread we retrieve value 2 that was pushed in the first thread, and before stack was modified, we actually see an empty stack in the second thread. So it's natural to expect here synchronization. So new notion of correctness that is suitable for weak memory model, it's atomicity per each object and preserving synchronization that is defined in that way. So it's suitable for this particular implementation depending on how strong guarantees it wants to provide. Problem is that there is no such automatic tool that can check this notion of correctness automatically. So we are providing a new tool, RELINCHE, which is the first tool for checking relaxed linearizability of concurrent data structure fully automatically. It's based on model checking. It automatically can explore tests of bounded size. It scales up to 7-9 operations. And we actually found violation in popular on GitHub library libcds. In the rest of my talk, I will tell you how we answered on two questions. First is how to define such relaxed specification, and how then verify implementation against it. Let's start with first one. In the beginning, we just take standard implementation of queue for single thread that has infinite array of nodes, counter for beginning and end of the queue, and its standard way to make it linearizable, just wrap global lock around it. But problem that this global lock will introduce too much synchronization. It's actually expose synchronization between each pairs of method calls. Instead, we will use partial lock, which was introduced on POPL'23, and this still ensures atomicity, but does not expose any synchronization to the client. This is artificial device that we cannot use for implementation. But it's very nice abstraction for defining specification of such relaxed data structures. So if we want to define somewhere synchronization, we actually can use C11 atomic accesses. On this example, you can see that we added acquire and release accesses to accessing elements of nodes array. And only operation enqueue and dequeue that is accessing same index in the array will have synchronization. And only their synchronization should be preserved by implementation. In other cases, for example, if we have pair of two enqueues, no synchronization is expected. So this is how our specification looks like. Then let's try to verify implementation against it. And we split this question in two. First, we will try to verify our implementation against one test, and then try to solve bigger problem, how to check exhaustively all possible tests. So for one given test, our algorithm looks like this. We have two phases, and first phase, we are analyzing specification. For that, we will run model checker on the given test with the specification and collect all behaviors that it exhibits. For example, we have this test client, and model checker will give us execution that is represented by, for example, it could be represented by execution graphs. And important things that is recorded, it's return values of methods and synchronizations that should be preserved by implementation. On the next phase, we will run model checker on the same test, but with implementation. And again, model checker is able to enumerate all possible executions of it. And for each execution, we are checking that there is at least one execution of the spec that match to this. It should have same return values and has less or equal synchronizations. So for example, this is one of execution graph of implementation that could be observed. And we see that there is actually behavior of the spec that have same values and preserve all synchronizations that it has also preserved by implementation. And it's important to allow implementation have more synchronization than it's in the spec. This is how we check one particular client, but how to check all of them, because of course checking just one is not enough. We just check this client, and we should also check this, and there's many more clients. So we can just try to run our tool on all of them. But it doesn't scale well, because number of clients that we have to check grows very fast with increasing number of calls of methods of data structure. Instead, we will try to do something smarter. We observed that this client in the top can see empty marker 1 and 2 values. And other clients can observe just some subset of these values. So we called this client in the beginning as the most parallel one. and other clients we will consider just as some extension of this most parallel client. So we can leverage this observation to running our tool on most parallel client and observe all possible executions of all extensions at once. But it doesn't work straightforwardly. For example, imagine that we have such implementation that have some bug, it's just trivial implementations that always return empty marker. If we just run our most parallel client on this implementation, we see empty marker, but it looks fine because we can justify this value by first executing dequeue. But if we run this implementation on the extension of most parallel client that forbid execute first dequeue, it's actually this extension reveals the bug. So conclusion that checking extensions of most parallel client is really necessary. We cannot avoid it. But we can still use most parallel client to explore all executions. And then for each output, we will calculate minimal set of extended client that render this output erroneous. And then we can use this information to actually check all behaviors of implementation that extended client that forbidding this output cannot observe it. So this is, now I show you how our final algorithm working. And first phase, we're analyzing specification. We're running model checker on most parallel client with the specification, collect all behaviors, and then for each output, we will calculate minimal set of extensions that forbid this output. How exactly we'll calculate this set, I'm inviting you to read in the paper. On the second phase, we are checking implementation, running model checker on the most parallel client with implementation, checking that each execution graph have some matching execution graph of the spec, and then we're checking that output of this implementation graph cannot be observed by the extension, by forbidding extension. So it makes it inconsistent. For example, this is graph that could be observed by the implementation, buggy implementation that I was showing you before. We are adding this extension and check is it still a consistent graph. If it's still consistent, so we found a bug that could be observed by this extended client. So in the end, how does it scale? On this chart, we can see time of checking most parallel client depending on size from 2 to 9. And first fact that we can see, oh yeah, it's for just for Michalis code queue implementation. So we actually checked most parallel client of size 9 just in 15 minutes. And that means that we checked that our implementation is correct under any client that have less than 10 operations with any possible order between them that is forced by client. And also another fact that you can notice that time of enumerating of all executions of most parallel client is bigger than our additional checks of refinement that we introduced. So our additional checks are not bottleneck. So to sum up, what we learned today, we can use model checking for checking relaxed linearizability of concurrent data structure automatically. We can use partial lock to expressively define specification for such relaxed data structures. We can use most parallel client to verify all clients at once. And this approach is feasible enough to check, to find violation in popular libraries like libcds. Thank you for your time and attention.
Okay, we have plenty of time for questions.
Hi, what was the bug that you found?
Yeah, I can show you. Thank you for your question. So it looks like like this. It's some client where we have some output which cannot be explained by any linear order. But in the documentation, they say that this data structure is linearizable.
Thanks.
Okay, we have another question on this end.
I just have a question about the semantic of your partial lock.
Sir, can you repeat?
Can you? Okay.
Yeah.
I had a question about the semantic of the partial lock, because the way you presented it, it was just like this block is atomic, but then it can be reordered with other instance of the same partial lock. But if you do that, you seem to still expect that if you do multiple calls to the same object that are bounded by partial lock, they cannot be reordered.
Yeah.
So does that mean that you still have a concept of program order between partial locks?
So yeah. So question is what is exactly semantic of partial lock? So this partial lock introduces synchronization that can be seen only by library events. But it's not exposing any synchronization outside.
Okay, so yeah, so that means that multiple partial lock from the same library will be synchronized, but not with the others.
I mean, yeah, they're synchronized, but only from the point of view events of library. Yeah. That is used for implementation of data structure.
Okay.
Other questions? If not, let's thank the speaker again.
Thank you.